Hello everyone, I welcome you all to this new tutorial. In this video, I will be talking about some basic rules for encoding molecular structures into Smiles notations. I will also talk about certain online tools and softwares for converting molecular structures to Smile strings. Then we will switch gears and I will show you how you can use these Smile strings and convert them into molecular structures using Rdkit. So let's get started. SMILES or Simplified Molecular Input Line Entry System is a notation that allows a user to represent a chemical structure in a way that can be used by computer. It is a linear notation where each atom and bond is represented by a specific character or set of characters. SMILE strings are human readable and can be used as input for various cheminformatics applications. So basically, SMILES is a text notation of molecules for computers to understand. Let us start with representing atoms in SMILES notations. Generally, atoms are represented by their atomic symbols. For example, elemental carbon is represented by its atomic symbol C in square brackets. You can do the same for other elements such as sodium, just use their atomic symbol in square brackets. You can also represent isotopes in SMILE strings. All you need to do is grab the atomic mass followed by atomic symbol and all of it will go in a square bracket. Next, I want to talk about how you can represent hydrocarbons, mainly alkyl chains, as SMILE strings. Single bonds and hydrogens are typically not explicitly shown. Double bonds are represented by equal to sign and triple bonds by this hash symbol. Branching is generally taken care of by placing the side chains in parentheses. Charges are indicated by positive sign for a positive charge and negative sign for negative charges. The charge is typically placed after the atom. So let us just understand this with the help of an example. This is a methane molecule and we can represent it in SMILE strings with just the atomic symbols without any hydrogens. Similarly, ethane can be represented by 2 carbon symbols. Similar is the case with propane, which can be represented by 3 carbons. Next, let us talk about branching. So this is isobutane. Here you can see this is the main chain here and we have this CH3 on the branch. So what we are gonna do is represent this main chain with 3 carbon atoms, and the branching will also be represented by carbon but in parentheses and without any hydrogens. Similar is the case with isopropanol. This is the main chain represented by 3 carbon atoms, and this OH is in the branch, which can be represented by the symbol of oxygen in parentheses. In case we have a double bond in a molecule such as this, which is isobutylene, all we have to do is add this equal to sign between these 2 carbon symbols. The rest of the process is similar. Triple bonds are represented by hash symbol. So this is propyne. All we have to do is add this hash symbol between carbon atom 1 and 2. In case we have charges in a molecule, such as the one in here, all we have to do is put the carbon along with the hydrogen and positive charge in square brackets. Rest of the carbons stay the same. Similarly, in this molecule, this is the main chain and this NH3 is in the branch. So we are gonna be representing this main chain with 3 carbon hairs. Now this NH3 is in the branch, so we will put this in parentheses. Also, this is charged molecule, so we have to explicitly mention the hydrogens as well as the charge along with this nitrogen atom in square brackets. Now let's talk about cis and trans isomers. For trans isomers, you use the forward slash or backward slash characters before and after the double bond. For cis isomers, you use the forward slash character before the bond and backward slash character after the bond, or vice versa. So let us just see this with the help of an example. This is transalkene with 4 carbon atoms in it. So we are gonna be writing their atomic symbols. The double bond is between carbon atom 2 and 3, and we have added equal to sign in between these two carbons. Now for representing this trans geometry, as the rule says, we have to use either of these characters before and after the double bond. So here I have used forward slash before and after the double bond. Now instead of forward slash, you can also use backward slash. They represent the same structure. In case of cisalkene, the only difference is that before the double bond we have to put this forward slash character, and after the double bond we have to put the opposite one, the backward slash character. Or you can do vice versa. You can put the backward slash before and forward slash after the double bond. Next I wanna talk about representing rings and aromatics as smile strings. Cyclic structures are represented by breaking one bond in each ring. The bonds are numbered in any order, designating ring opening or ring closure bonds by a digit immediately following the atomic symbol at each ring closure. Now let us just suppose we want to have a smiles notation of this molecule, which is cyclohexane. Now as you can see here, we have 6 bonds in here, and I have numbered each of this bond from 1 to 6. Now we are gonna hypothetically breaking the first bond over here. Since this is the first bond that we are breaking, we are gonna number these 2 carbons as C1, and we are gonna leave the rest of the carbons as such. Now let's just understand this with another example of tetrahydropyran. Again, it has 6 bonds and I have numbered them. And let us just assume you wanna break this bond over here. And in this manner, this carbon and this oxygen would be numbered as C1 and O1 respectively in the smile strings, and rest of the chain would be represented by just simple carbons without any hydrogens. Now one thing I want to mention here is that you can also break this bond over here, and you can number these as C6 here and O6 here. That would represent the same molecule. In case of piperidine, the procedure is same, except that we have to explicitly mention the hydrogens on the nitrogen in square brackets. Now let us talk about aromatic rings. Aromatic rings such as benzene are often represented by lowercase letters. Here we have a benzene molecule. The procedure is similar to that of saturated rings, except that the atomic symbols are in lowercase. Now you can also represent benzene in uppercase letters. In that case, you have to explicitly mention these double bonds with equal to signs at alternate positions. In case of aniline, we have benzene ring over here, which would be represented in a similar manner, and this NH2 will be represented by its atomic symbol in uppercase letters. Now in case the nitrogen is within the ring, for example in pyridine here, this nitrogen would be represented by its atomic symbol in lowercase letters. Next I want to talk about stereoisomers. Let us try to understand this with the help of an example over here. This compound has a tetrahedral carbon in it, and if you want to represent this racemic molecule as a smile string, first you have to identify the main chain over here, which is this one, NH2C, carbon of the acid, and OH. Now we are gonna be representing this main chain with their atomic symbol without any parenthesis, and that's what we have done here. This NH2 is represented by nitrogen, this tetrahedral carbon by this carbon. Carbon of this acid is here, and this OH is represented by O. Now we have three branches here, fluorine, CH3, and this carbonyl carbon, and we have represented them by their atomic symbols in parentheses. Now next question is, how can we represent its stereoisomer? Now let's just have a look at the rule. It says, looking at the chiral center from the direction of the from atom as per atom order in SMILES. So basically it's saying that first we have to look at this chiral center over here from the side of the from atom. And what is this from atom? It is the atom which comes first in priority as per the atom order in SMILES, and we have seen here that nitrogen comes first in the priority. So what we are gonna do here is that rotate this molecule in such a way that this nitrogen is in between this carbon and our ice, and we can do that by rotating it at 90 degree. After rotation it would look something like that, where this CH3 group, which was below the plane, would come to the left side, and this fluorine, which was above the plane, would come to the right side after rotating in the clockwise direction. At this point we have to number these atoms according to the priority rules. Fluorine would be the first priority, carbon of the acid would be second, and carbon of CH3 would be third, and they are listed in anti-clockwise direction. And according to the rules, we have to add this add character if these three atoms are listed anti-clockwise, and you can very well see that these atoms are in fact listed in anti-clockwise direction. So what we are gonna do is, we are just gonna add this add character after the chiral carbon, and both of these need to be in the square bracket. Once we have the SMILES string of this particular enantiomer, we can easily figure out the SMILES string of the other enantiomer where methyl is above the plane and fluorine is below the plane. In this case, on its own, the atoms would be listed in a clockwise direction, opposite from what we have seen here, and in this case all we have to do is just add this add character 2 times. Next, let's talk about some inorganic compounds and salts. Water can be represented by the atomic symbol of oxygen. Ammonia can be represented by the atomic symbol of nitrogen, and these need to be in capital letters. NH4 positive ion would be represented with their respective atomic symbols along with the number of hydrogens and the respective charge, and all of this need to be in square brackets. If you want to represent sodium chloride, you have to put just the sodium in square brackets followed by chlorine. In case you want to represent sodium chloride as ionic species with charges on them, you have to put both the atomic symbols in square brackets along with their respective charges, and these need to be separated by a dot. For sodium acetate, which is an organic compound, again we need to find out the main chain, which is over here CH3 C double bond O, and we can represent this main chain with their atomic symbols without any parentheses here, and that's what we have done here. Next, this ONA is in the side chain, so we are gonna be putting this in parentheses, and sodium will be represented in square brackets. Next, if you want to represent sodium acetate in its ionic forms with respective charges on them, then again the procedure is similar. It's just that then sodium would be a separate entity with its atomic symbol along with the positive charge in square brackets, and these two notations are joined by a period sign. We can also represent reactions using smile strings. So this is the imitation of benzoic acid, and these are their respective smile strings. Now for representing reactions as smile strings, all we have to do is combine all three in one smile string, where the smile strings of the reactants are joined together with a dot in between them, followed by two forward symbols, and then the smile strings of the product. So this smile string as a whole would represent this chemical reaction. In case you have reagents in your reaction, here this is DCC and this is the smile string corresponding to this molecule. All you have to do is add this reagent in between these two forward symbols. So this was all about how you can encode molecular structures into smile strings. Next, I want to talk about some of the limitations that these smiles notations have. Multiple valid smiles notations can exist for a single molecule. This arises due to the inherent flexibility of the smiles language and the fact that it focuses on representing the molecular structure and connectivity rather than providing a unique identifier. Smiles typically does not explicitly represent hydrogen atoms, while implicit hydrogen counts can be determined based on valency rules. The absence of explicit hydrogen information can be a limitation. It lacks the ability to represent the actual 3D structure of the molecules, including bond angles and dihedral angles. Representing large cycle structures such as macrocycles in smiles can be challenging, and the notation may become cumbersome or less intuitive for such cases. Next, I'm gonna be showing you some of the tools that you can use for converting molecular structures into smile strings. For this purpose, you can use commonly used software such as ChemDraw. I have opened up a window of ChemDraw here, and what I'm gonna do here is draw an organic molecule. This is phenol here. What I'm gonna do here is I'm gonna select this molecule and I'm gonna go to this edit and copy as smiles, and I'm gonna be pasting the smile string over here. So in this way you can generate the smile strings of any molecule you want. Since this is a proprietary software, in case you don't have it, you can use some online tools. cheminfo.org is one such online tool which you can use for generating smile strings from molecular structures. I have the molecular editor open here, which is available on this website. I'm also gonna be providing you the link of these websites in the description below. So what I'm gonna do here is I'm just gonna draw phenol molecule here. And down here you can see the smiles notation, which you can copy and paste wherever you want to use it. Similar to cheminfo, there is another website, rcsp.org. Right now I am in this chemical sketch tool section, which has this molecular editor, and what I'm gonna do here is draw the structure of the compound for which I want to have the smiles notations. So this is phenol molecule here, and down here you can see its smiles notation. Similarly, there are many other online tools out there which you can explore on your own. Next, I'm gonna be taking you to Google Colab Notebook, and I'm gonna be showing you how you can use these smile strings and convert them into molecular structure using Rdkit. I am gonna start off by installing Rdkit using pip install Rdkit. After it has been successfully installed, I am importing chem from Rdkit and draw module from rdkit.chem. Pandas would be used for loading Excel files. So let's go ahead and run this. Now in order to read these smile strings in Rdkit, the First and fundamental step here is to convert these smile strings into molecular objects using this chem module and mole from smiles method. I'm gonna be storing this molecular object in a variable called m, and I am gonna be visualizing this molecular object using draw module and mold to image method on it. So let's go ahead and see what this gold symbol in square bracket represents. So like I mentioned in the tutorial, if you wanted to just represent atoms, you can just represent them with the atomic symbol in square brackets. Next, let's talk about alkyl chains here. I mentioned in the tutorial that branching is generally represented by adding parentheses to the atomic symbol. So let's run this and see how our molecule looks like. So this is very obvious. These three carbons are in the main chain and this carbon is in the branching, so that has been put in parentheses. For alkenes, we generally represent the double bond with equal to sign. So let's run this command. So this is isobutylene here with double bond between these two atoms has been represented by this equal to sign. Triple bonds are represented by hash. So there is a hash in here. So basically that is a representative of propyne. Next, I told you a charged species can be represented by the atomic symbol along with explicit hydrogens and the charge on it within square brackets. So let's run this command and see our output. So this is basically a carbocation here and this carbon over here has been represented in here. I told you cis and trans compounds can be represented by forward and backward slashes. So let's just run this and see how our molecule looks like. So this is trans butene, and I also told you you just need to be consistent. Either it has to be forward slash or backward slash. So let's just replace this with backward slash and see our output. So it has given us the same result. Similarly, for cis alkene, we need to replace this one with a forward slash. So let's change this and let's see the output. So you can see here we have a cis alkene over here. Cyclic compounds are generally represented by breaking one bonds and mentioning the digit after the atomic symbols where we have broken that bond. So let's run this and see our output. And I told you we are just gonna break this bond here and gonna number this as C1 and oxygen as O1, and it could be C6 as well. So let's replace 1 with 6 and run this. So you can see we have the same geometry. Again, it does not really need to be 1 or 6, it could be 3 as well. So I have added 3 instead of 6, so let's run this. So again we have got the same output. Next we talked about aromatic systems. So let's first run this command and see our output. So this is aniline here. The aromatic carbons are generally represented by lowercase letters, and this is what we have over here. And in case this heteroatom or this functional group is outside the ring, that's generally represented by an uppercase letter. Again, if we have instead of nitrogen, if we replace it with O, it would probably be phenol. So let's run this. So we have got phenol over here, and again this oxygen can be over here as well. Okay, now let's just move on to stereoisomers. Again, let's run this command first. Now you can see here in this case this methyl is above the plane, and if we add another add character here, it would inverse the stereochemistry. So now you can see here this methyl group is below the plane, and I have already talked about how would you know whether there needs to be a single add character or a double add character. Next, I want to show you how you can remove duplicate smiles. While we were talking about the limitations of smile strings, we talked about how a single molecule can have multiple smile strings, and that can be a problem while analyzing these molecules. So let me just go ahead and uh, load this smiles Excel file which has the names and smile strings of few molecules. So let me just run this command and have a look at our dataset. So this is our dataset. It has around 10 molecules in it. These are the names of these molecules and these are the smile strings. Now if you carefully look for a single phenol molecule, we have 4 different types of smiles. For this 2-pyridinol, we have 3 different types of smiles or 3 different smiles notations, and for trans-2-pentene we have again 3 different smiles notation, and that could really cause problem because Python is gonna recognize them as different molecules. So let's call a unique function on this name and smile strings. So we have 3 different types of molecules in here: phenol, 2-pyridinol and trans-2-pentene, and but smiles, we have 10 unique smiles. So what I'm gonna do here is that convert these smile strings into molecular object and visualize them using draw.moles to grid image method. So let's run both of these commands and visualize our molecules. So now you can see that these smile strings are giving us the same phenol molecule up here. We have 3 different types of strings, but just 2-pyridinol in here, and 3 smile strings for trans-2-pentene. Now what I'm gonna do here is that in order to remove these duplicate smiles or duplicate data points, what I'm gonna do here is convert these into canonical smiles. So what are canonical smiles? Canonical smiles refers to a specific way of representing a smile string for a given molecule. The concept of canonicalization is important in smiles to ensure that chemically equivalent structures are represented by the same smile string. In other words, even if a molecule can be drawn in different ways, the canonical smiles should be unique for that molecule. The process of generating canonical smiles involves applying rules to choose a specific representation among the possible isomers or tautomers of a molecule. This ensures consistency and helps in comparing and searching for chemical information in the database. The point I am trying to make here is that a single molecule can have multiple smiles because it has flexibility of rules. For example, this benzene ring over here can be represented in uppercase letters with the symbol of equal to sign at alternate positions representing double bonds, whereas it can also be represented in lowercase symbols with no double bonds. Now in the dataset that you are using, it's possible that the smile strings that you are using of the molecules has been extracted from different sources. For example, it's possible that a ChemDraw would give the smile string of benzene as this one, whereas ChemSpider would give the smile string as this. So that can lead to duplication of smiles. Therefore, if we make the rule stringent, the possibility of duplicate smiles is reduced. Therefore, in summary, I would say smiles is a general notation for representing chemical structures, while canonical smiles is a specific standardized representation of a molecule using the smiles notation to ensure uniqueness and consistency. So let's just have a look at our dataset again. Now this is the name column and smiles column. What I'm gonna do here is I'm gonna create an empty list here with the name can_smiles. Then I'm gonna run a for loop where it will iterate through each smile strings, and in this line of code it will convert the smile string into molecular object, and in the next line of code it will convert it back into the smiles notations. Basically in this step what we are gonna get is canonical smiles. In the end I'm gonna be appending this canonical smiles to this list over here, and what I'm gonna do then is I'm gonna be adding a column to this data set with the name can_smiles, which have the canonical smiles of these molecules. So let's run this and have a look at our dataset again. Now you can see that along with name and smiles, we have another column called can_smiles, and as you can see that these 4 data points, we have different smile strings, but we have the same canonical smiles. Similarly, for 2-pyridinol, we have different smiles here, but same canonical smile, and similar is the case with trans-2-pentene. Now what I'm gonna do here is, just with one line of code, I'm just gonna be removing these duplicates, and in the end I'm expecting to see just 3 data points. First one belonging to this phenol molecule, second one to this 2-pyridinol, and the third one for this trans-2-pentene. So what I'm gonna do here is use this drop_duplicates method, and I'm gonna be using subset of can_smiles. So let's run this and have a look at our data set again. So now we have kind of filtered our data set, and now we just have these 3 data points without any duplicate smiles, which we can use further for our data analysis. And in the end, I'm just gonna be dropping this smiles column because we don't really need this anymore. So this would be our final data set. In case you have any questions, please let me know in the comment section. Thank you for watching.